So let's begin with this first example. Suppose that a saleswoman has to visit 8 different cities. She must begin her trip in a specified city, but she can visit the other 7 cities in any order she wishes. How many possible orders can the saleswoman use when visiting these cities? Okay, so let's start off by making some notes here. It says that she's visiting 8 different cities, but soon after that, here, let's make that a little smaller. Soon after that, it says that she's going to begin the trip at a specified city, and that only the remaining 7 can be in any order. So at first glance, it looks like the number of objects that we are working with would be 8, but continuing to read the example, we could see that the number of objects, which in this case would be cities, is 7. And we are going to arrange all 7 of these cities. And we're not actually going to list out every city and arrange them all out, but that's the idea. The idea is that all 7 of the cities that we have are going or can be arranged in one way or another. All right, so let's think about this. So suppose we have maybe our first stop. We can label this S1. And then we have our second stop, S2, our third stop, our fourth stop, our fifth stop, our 6th stop, and then our 7th stop. Remember, the first stop is already specified. We're going to assume that the first stop is taken care of. We don't really need to know the first stop. It's kind of just extra information. So we're really focusing on the remaining 7 stops. Now, out of the remaining 7 stops, the saleswoman could stop at maybe city 1, then city 2, maybe skip over city 3, go to city 4, come back to city 3, then city 5, city 6, and then city 7. Now that is just one possible combination. That is just one possible arrangement. Now let's kind of think about what we need. Remember, we want to know the number of possible arrangements, the number of possible orders. So I'm going to rewrite these spaces once again. Our first stop, our second stop, and so on. All the way down to our 7th stop. Just going to scroll down here a little bit. And let's think about that multiplication principle. Remember, the multiplication principle says that we can multiply the distinct number of choices every time we have a choice to make. So for this example, we can write down 7 in our first entry, because out of all the cities in our first stop, we can choose one of the 7. We can pick one of the 7 to stop at. Now that we've already got one of the 7 out of the way, our second stop will have to be one of the 6 remaining cities. And we can continue this pattern, right? Out of all of the remaining cities for the third stop, we only have 5 cities left to choose from. Like I said, we can continue this pattern until we only have one city left to choose from. And using the multiplication principle, we do end up with 7 times 6 times 5 times 4 times 3 times 2 times 1. And that would equal 5,040. So there are 5,040 different orders in which the saleswoman could go to each city. But let's explore what we have here. Let's think about this arrangement. We have 7 times 6 times 5 times 4 times 3 times 1. Well, some of you might recognize that this is in fact 7 factorial. All right, 7 factorial says that we'll start at 7 and multiply each receding number, or rather each receding whole number, so 7, 6, 5, until we get down to multiplying to 1. Alright, well, we're going to examine this a bit more. Now, let's think about what's happening here. 7, 6, 5, down to 1. Well, 7, that's just 7. 6, how does that relate to 7? Well, it is 1 less than it. 5, well, that would be 2 less than 7. Now, if we continue this pattern, remember the last number here, that last whole number, that last digit is 1. Now, if we can continue this pattern, we're going to be subtracting by 2, then by 3, then by 4, then by 5, up until we end up with 7 minus 7, which is 0, and then we can add the 1. So right now we're just kind of examining what we have. We're thinking about what this factorial is and what it's telling us. Remember, this is a type of permutation. And because it is a type of permutation, let's just remind ourselves, this is a permutation. This is a permutation of 7 objects. We could think of this as a 7 permutation. Of 7 total objects. And again, in this case, our objects are cities. All right, well, let's generalize this a bit. I'm going to introduce a notation, P, N, comma, N. Now, this notation is going to signify this, that we are looking at a permutation of n total objects and we're going to permute n of them, or the second number. This number would be the number of objects to order or arrange. Okay, now let's come back to this formula that I'm writing out here. Again, we have P parenthesis N comma N. The first number is going to be the total number of objects. The second number is going to be the number of objects that we are ordering. Now for this 7 permutation, we are ordering all of the objects, so that is why both of these variables match. We have N and N. So if I generalize this using what we've written up above here, the 7 times 7 minus 1, we could think of this as 7, or rather, let me back that up. We could think of this as n, right? We're trying to generalize this, times n minus 1, times n minus 2, all the way down until we have n minus n plus 1, which of course this is just 1 times 1. And this turns out to, as we saw above, to just be n, oh, running out of room there, n factorial. So we have some space down below. I'm just going to write out our kind of general conclusion here. If we are taking n total objects and arranging all n of them, let's write that, all n of them, then the n permutation could be rewritten as Pn, n equals n factorial. So if we are taking all of the objects and arranging all of them, what we are really just finding is a factorial. Okay, and that is all for this video.